bit of context as to like, oh, now it's recording. I'll start again. Hey, everyone. Thanks for joining Paper Club. So before jumping into the paper today, I wanted to give a bit of background as to like why I chose this paper, why I thought it was cool. I must admit, I actually chose, this paper was written by a team at this company called Leap Labs, which happened to be 5 minutes down the road from where we are at Implant. I met them at like an event a few months ago, and they presented some of the work that they're doing, and I thought it was really cool. And so I thought, hey, this would make great topic for Paper Club. But beyond that, why I chose this paper is because it's actually conceptually quite simple. Like the methods they use, I think, are not overly complicated. But the results are quite like profound, and I think it's a really cool paper as opposed to just thinking about how we get better and better models. It's a method that we can use to really question what our models are doing, how they're learning, and hopefully have like a better feedback loop so we can develop more unbiased models and models that generalize better in the world. This paper, oh yeah, for Peter.
And what does Leap Labs do? Like, are they a business? Are they a research lab? What are they? And what's their?
Yeah, they're a business, and they're commercializing basically this technology they've built. And so that as a business, they're building a product for model interpretability across different modalities. So not just this paper focuses on images, but I know for a fact they're doing images and text, potentially other modalities as well. And the best thing, or one of the powerful things about this model is that it's, or this method is it's model agnostic. So it doesn't matter like what underlying architecture you use. You can use this method to interpret how the model's learning. And also it's data independent. So they don't actually need to see any data in order to understand how the model's learning. So we'll dive into how that's done. But yeah, those are two important aspects of this interpretability method, which is it's model agnostic and data independent. And as I mentioned, the powerful thing about this is that you can, at a high level, how it works is it generates these things called prototypes. And prototypes is like the perfect image for a given class. So let's say you have like ImageNet, which has like dogs and cats and all sorts of things. You generate like the prototypical image of like a dog or a cat. And in doing so, you can understand how the model perceives what a dog is and what a cat is. And you can make some claims about what the model's learned or what patterns it's picked up. So, I mean, we know interpretability is powerful and important, especially in this world of like more and more black box models. AI is being put under the lens to be able to explain like decision making, especially like in the EU with GDPR. And so it's quite like crucial to understand how models make decisions. A lot of methods in the past, like SHAP and Lime, like these ones, work by work by looking at a set of data. So you have a set of data points, like a test data set, and understanding, classifying those, and then looking at what factors led those to being classified in the way they were classified. But that restricts you to looking at the interpretability of a subset of data points that you have access to. So what they're claiming here is that these techniques, it's more powerful to look at like, to have a global understanding of what the model has learned, rather than focusing on just the few data points that you have access to. And this is where feature visualization comes in. So as kind of it says on the tin, feature visualization are methods that you can use to somehow visualize different aspects of a neural network. So you may have seen in the past like images of like what does a neuron look at, and like what does a layer look at, and you can it starts to form more and more like abstract concepts. And you may have seen like deep dream in the past of like you you where you can use these methods to visualize like what it's doing at different layers, or how it's perceiving like a dog or things like that. So this builds upon that previous work, but it solves or improves a limitation of these methods in the past, which is that the images that are generated through feature visualization in the past tend to not be very representative of like real images. So that's what they say here, that like past research has said that the disparity between the sort of internal processing of the feature visualization, so the things we generate, as compared to other like what they call natural images, there's a large disparity. And they use this concept called path similarity. And you can think of path similarity as like how similar do the neurons in the network get activated compared to a real image of a dog. Let's say I'm going to keep using the dog example so you can apply to anything. So to sum it all up, they build on feature visualization, but they work on improving this limitation, which is that the images that get visualized aren't like that representative of like real world images. And so they try to create prototype images with that constraint in mind. So yeah, I kind of mentioned like a little bit about like the past work. The important part being that feature visualization is like it's a global interpretability method rather than locally to your data set. It's data independent, and you can actually in this paper they focus on maximizing the logits of a certain class, but you can actually change this to optimize for, like, for example, the activation of a particular neuron or a particular layer or a particular channel in the image. You can do this work at like many different levels, but what they've chosen here is like to focus on how do we create the prototypical dog for a computer or whatever class. Importantly here, they mention that they mention again this like path similarity problem, and they introduce the metric here. So they call it, they have this Spearman's rank order correlation. So every time you see SS, it's the Spearman similarity. And it basically compares like as I understand it, it basically ranks the neurons in terms of their activation and compares the order of neurons between two sets of input images. And so the idea being that we want to create an image that maximizes the logits for a class while maintaining high path similarity with the set of images that the model was trained on, or the set of natural images. And so this is what they call like prototype generation. And so here we get into like the formal definition of that. And so really, like, it is as straightforward as that. It's basically you want to optimize for the logits for a class while trying to maintain these constraints. So they implement these two metrics. So they don't just do the Spearman similarity to compare the order of the activations of the neuron of neurons, but they also implement an L1 metric because they claim that it's not just about the order, like the neurons that were activated, it's also the magnitude is important. which the L1 like preserves. And so what their assertion then, or like what they're trying to do in this paper to solve this problem of like similarity, is they're saying that so let me maybe talk about notation a little bit, because we're going to see these things like quite a bit. So you have this like I, which is the set of all possible like natural inputs. You can think of natural inputs as like real world images and captures of a particular class. And then P is the prototype, so that's the image that we're generating. And then the I here is like an individual image that we have. And so the claim here is that the L1 distance of the activations of the prototype compared to the average activations for this set of like natural images will be closer than the mean to any individual image. So maybe let me say that again, because that was quite a mouthful. So this here represents the like. Actually, let me zoom in a bit. So this here represents the average activations at any layer for a set of natural images. And these are the activations for the prototype at each layer. And the claim is that these will be closer than any individual image in our set compared to the average of all of these natural images. And the same goes for the Spearman similarity. So we want the activations of the prototype to be closer to the mean than any individual image in our data set. This doesn't hold true in like all cases, but it's like a sort of, I suppose this is kind of like a soft constraint or like a secondary objective that you're trying to maximize. Cool. By the way, I'm keeping an eye on the chat. So if there are any questions, please pop them in the chat or go off mute, and I'm happy to answer. Cool. So they give a couple of examples here to sort of tease us before getting into the experiments. So here they show us 3 classes in ImageNet, and at the top is the prototypes that were generated using their method, and at the bottom are the prototypes generated using the baseline feature visualization method. And in the brackets is the Spearman similarity of the prototype compared to the average of all natural images for that class. And so you can see that the Spearman similarity is much higher for their method than for the baseline method. And you can kind of see that like they're a little bit less like trippy. So you can see some like concepts that are being picked up. So in mosquito nets, you can kind of see like the form of like the mosquito nets, and like I actually don't know what an Alaskan Malamute is, but you can kind of see a face here.
I think it's like a husky.
Fruits. Is it? Okay. Yeah. So here's they compare their methods to the baseline, and then they go into a little bit more detail as to like, okay, what are the actual differences? So conceptually, like I mentioned before, it's the whole method. It's actually super simple. So what they do is you randomly initialize an image, and then the first step that they do is they create like a what they call a baseline image. And the goal of this baseline image is to balance, is that the baseline image should have a roughly equal chance of like falling under any class. So they make sure that it's not like biased as to any class. It's sort of it's minimizing, I think, the variance of like all of the different probabilities for all of the classes. And so that just makes sure that it's like a solid baseline. They pre-process the image based on like whatever the model expects. And then they apply affine transformations. And they mention that they do this because they, as a way of like regularizing the prototype generation. Yeah. That's kind of the same as it's the same as the baseline feature visualization method. And then they do the optimization. But note that there's another loss, and there's another loss input, or another input into the loss that's different to the baseline, which is this LHF. And this LHF, they mentioned down here, is a high frequency loss that penalizes large differences between adjacent pixel values. So they try to reduce this kind of like high frequency problems. And that's seen in the original feature visualization method, where if you try to optimize for just like the logits, sometimes it creates these like images that kind of looks like noise, but manages to optimize the logits. And so this is actually a way of like constraining it to generate, I think, more realistic prototypes. And that's, I forgot to mention, that's kind of also a primary difference between their method and the original feature visualization method, is that their method optimizes, it tweaks, it works on the pixels directly, whereas the feature visualization method first converts the randomly initialized image to like a Fourier basis, and then optimizes on that. Cool, thank you. Yeah, so I suppose that because they want to optimize the pixels in the image directly, then they have to add this like loss input to make sure that it doesn't generate like a kind of noisy high frequency image. Cool. So this is my least favorite part of the paper, because I think these plots are really weird and kind of gross. But I'll try to explain. I was staring at these for like 5 minutes, 10 minutes before I really properly understood what was going on.
For me, the confusing part was I was like, this is L1 distance and it's negative. But then I realized that they normalized it at 0. So
exactly.
0 is the mean.
It's so, yeah. I was like, what? Like how it's like negative is better. I was like, wait, I don't get how, but yeah, that's right. So the blue line, so the blue line is you can think of this as the average of every class image in our data set. Sorry, the average distance. Okay, sorry, let me start this again. So you have a data set and you compute the average of all of these, the average like activations at each layer. And then they normalize it such that the average distance between each image and the average activations, so the activations of each image to the average activations is 0. And the activations of images in the other classes to the average activations for that class to be 1. So effectively, they're comparing. But the reason they do this is because of their assertion here, which is that the distance between the prototype and the, let's call it the average natural image, will be smaller than the distance between any image in our data set and the average image. And that's kind of what we see here, right? So across, on the x-axis is the layers. So across the vast majority of layers, the L1 distance for the prototype is lower than the average of all of the images in our data set, and definitely the average of all images that are not part of that class. And this applies across ResNet and Inception. So they compare these two models. But it's not always the case, right? So at first, I thought that this optimization was kind of like a hard constraint, but then actually it doesn't seem to be like a hard constraint. It seems to just be like it's just
I think my understanding was actually that constraint above falls out from their methodology of optimization. Like the pipeline leads to an example, like a prototype, where the average activation distance is less than that of all the examples. So I was actually thinking maybe this is this is an interesting result of their methodology, that it leads to this constraint that they're talking about, but it's not clear, in my opinion, in how the paper is written, that this is the case. Because when I was reading it, I had the same interpretation as you, that they were using this constraint to optimize the image that they were generating, the prototype. But then if you, in the pipeline, you don't see that constraint anywhere. But maybe it is. Right. I don't know. So that's that would be a point of, so that could be an area where they could, it would be good to get some clarification.
Yeah. It's a good point, actually. They don't specifically mention that they optimize for it. They basically, I assume that they include this high frequency loss as a way of getting there. And then also in the appendix, they talk about how, so they have these random transformations, which are rotation and scaling, and they show how they tried different combinations of transformations and how that improves the path similarity. So it looks like they're basically tweaking the hyperparameters of their method in order to improve the path similarity, but maybe not optimizing directly for that. Yeah, it's a really good point. Cool. So yeah, they mentioned, as we showed in the diagram, basically the whole point of this diagram is to show that it's below, that the distance is smaller. It's really interesting. I found that it seems to be much smaller in the first, the earlier layers. Yeah, presumably it's doing something different there. So here they go into a little bit the sort of methodology they use to generate these metrics. I don't think it's particularly interesting or important. Well, it is important, but not particularly interesting. But they basically they collect 100 random images for each of the classes, and then use those to calculate this kind of average natural image. And yeah, they show here again how average experiment similarity is higher for the prototype than for individual images, natural images. Oh yeah, sorry. Here they're comparing again. That's just sort of hammering home the point that like the path similarity for their method is much better than the than the baseline method, because the baseline method only beats the similarity at like the final layers, whereas their method seems to be sort of consistently above the average.
Gerard, there's a question in the chat, which is, why do you think the L1 distance seems to be higher for the top layers? Could this be an optimization artifact?
Yeah, it's a good question. I don't have like an intuition for why it would be.
One thing that's true is that, well, actually, I think these are CNNs. So, and with CNN, and these CNNs have like pooling layers. So like the earlier, I hope I'm correct here, but the earlier layers have basically smaller features in terms of the image, and the later layers have like larger features. They're looking at like larger parts of the image. And also the earlier layers have much more like basic features. Like I've seen visualizations of what are the features that CNNs pick up on in the first layer of an image, and they're really simple. They might be like, if there's like a vertical line in terms of contrast, like between 2 pixels, or if there's a horizontal, or all these things. So maybe it has to do something with that, like how earlier on the features are simpler or smaller or something along those lines. But I also don't have a good intuition for why this is happening. Just adding more ideas.
Yeah, I suppose like if you think about what it's doing, it's like it's trying to create this like average, almost this like average image of like what that class is. And I wonder if like if you have 100 images of a class, let's say 100 images of a dog, they're all quite different. They're probably all quite different. And I imagine the activations of those images in the first layers might be quite different, because they might be fired by like slightly different things, like different lines or different patterns. Whereas as you go down the network, it starts getting into more abstract concepts. So for a dog, it might see like a snout or like ears. And therefore, those images, even though they're all quite different, the activations will be getting more and more similar, I suppose, in the later layers, because you start dealing with these more abstract patterns. Whereas in the first few layers, they're probably activated by like a bunch of different. There's more variance, I guess, in the activations I imagine at the beginning within the class. I'm just guessing as well. Cool. So this is like, we've gone through the method, but like actually the cool part of the paper is like, what does this allow us to do? So as a reminder, like now we have this method where we can generate what these like prototypical images of a class look like. And we can use those to really understand like what have these models learned about that class. So they show kind of a few different ways that you could use this to understand your model. So they picked out these 2 classes, which are we know are super different, but the prototype of these images are actually super similar. So you have like an academic gown, and then the second class is a mortarboard. And like you can see here that like these two, just for some reason, like the model seems to, the prototypical images are quite similar. And so they show like how you could use these prototypes. The first thing they show is like their hypothesis that using the academic gown prototype, you can make an assumption that the model will have an easier time predicting academic gown when there's lighter skinned people in the image than darker skinned. And the reason they make that hypothesis is because you have like the only sort of what you could feasibly think of like as a face in this image seems to be lighter skin. And so they generate like an experiment to do that, where they gather images in the academic gown class, which have lighter skin and darker skin people, and show that indeed like the accuracy is quite a bit higher when you have lighter skinned people compared to darker skinned people. And the probability of predicting academic gown in those cases is also higher. So you can, just by looking at the image, they managed to think of this experiment they could run to show a bias in the model and validate that the bias exists. The second hypothesis that they, from looking at these images, is that in the mortarboard example.
What is a mortarboard? Sorry, I didn't know what it was, so I was confused.
Let's get an image up. It's the actual, it's the cap that's used in the graduation cap.
Okay. Wow, these are very similar. Like I could see how a model would struggle to classify these two. Because isn't a mortarboard part of a gown? No.
Yeah, it's like, it's probably like seen in the images in the data set where academic gowns are present as well. So understandably, they probably would be quite similar images. But yeah, so they basically say that you like they make this claim. I don't know. I guess another criticism of this paper is these hypotheses and these examples seem really handpicked. So it's like very illustrative, but you know, you wonder whether like how many different like experiments they came up with to try out, like to validate that this method is useful. Because what they say here is that by like looking at the differences in these prototypes, the academic gown one has a better representation of a face than the mortarboard one. I'm like, I don't see faces. I guess you can make that claim, maybe. Like it kind of looks like there's not as much of an image of a face, and so they use that to say that like when there's a face present, that might activate the neurons to classify this as an academic gown rather than a mortarboard. And indeed, yeah, they show that.
Yeah, actually, one thing I would have liked to ask the authors along these lines is that, like the misclassification of people of color in these models specifically, because they're quite old, is a well-known phenomenon. So I think it'd be more compelling if they could come up with a new bias in the data set that was for these models. And also then the comparison between mortarboard and academic gown, we've already pointed, like we can logically see why that would be an issue. So it would be, they're not pointing out unknown relationships. It would be more compelling if they were, in my opinion.
Yeah, I completely agree. When I saw their presentation, the example that stuck with me, which is not in this paper, was they showed their method on a model that was where the classes were actions. So imagine like dancing, fighting, running, jumping, like whatever it is. And one of the interesting biases that you could spot in there. There was the dark skin, light skin one that was present because in the fighting example, the limbs seem to be darker skinned. And so there's a sort of bias where for darker skinned people, you'd have a higher prevalence of like predicting fighting, which is a bias. But the other bias that I thought was interesting, which is not as like well documented, is in the running picture, the bottom part of the image was kind of greenish, which suggested that there was a lot of running pictures like where people are running on grass. But they said that like indeed there was a bias where it had an easier time predicting running for images where there's grass present than when you're running on like pavement or cement or whatever. So that was another example of a bias that is not sort of this kind of demographic bias. Yeah, so they show, yeah, like I said, they showed like the mortarboard and how much more accurate it can be predicted without a face than with a face, because it seems to just like not have a good representation of a face in the prototype. So you can already see like when you're developing these models, having this feedback mechanism is really useful to say like, oh, maybe I need to like find more images to help it learn how to deal with faces better, or like maybe I need to look at my images because there's a bias present in them and things like that. So it gives you another tool in your toolkit to do like model iteration. But I guess another, so that's like kind of one cool use case. But I think a really cool use case of this is like the verification of like models as like an audit tool. And it's a cool audit tool because you don't need to collect images to use this method. You just need a model with weights, and then you optimize based on that model with weights, and you get these prototype images. And then you can make claims about the model, right? You can inspect for like different kinds of biases, and you can spot failure modes like much more easily. So you can see where two classes are like look super similar, or the distance between the two prototypes are small. So you can already start to understand like, okay, there's probably going to be misclassification of these classes. What do I do about that? How can I patch those or improve those? And yeah, that is the paper. One thing that I thought was maybe, yeah, I'll touch on a little bit is this like, I mentioned the transformations as a way of regularizing the model, but also the like high frequency penalization. So, you know, this like argument to the loss function, which penalizes neighboring pixels having slightly different, like largely different values. And you can actually see how the impact that has. So if you don't regularize, you get these kind of like noisy, not really clear images. But as soon as you regularize, you start getting more like actual concepts, in this case of like a goldfish. And they show a bit more of like, oh, these are like the raw Spearman similarity values, they're non-normalized. And it's quite interesting that like I thought it was quite interesting that the difference between images of the class that we care about and images of a different class, the Spearman similarity is like super tight. It's like super close. And I thought that was kind of interesting. So like, to me, and I'd be curious to hear everyone else's thoughts, because like to me, that says that until you get to the final layers, the things that are activated in the network are actually quite similar for any kind of image. Like not just, it doesn't matter what class it is, like any kind of image activates the same neurons.
Yeah, that makes sense to me though, because it means that the model is learning like a visual vocabulary and just trying to like extract those features, and then in the last layer, they're trying to distinguish them. I've heard arguments that like a good way to think of a model for classification is like everything up to the last layer is a feature generator. And so it's just extracting features, and then the last layer is doing linear regression on those features. Yeah.
That's a cool interpretation. Any questions? Maybe I'll show. I don't know if they've got anything on their website. But I'll link it. I think they're still in like product development, so I don't think they have anything live yet. But I know for a fact that so this work is on images, but I know that they're working on similar methods for language models as well, which will be kind of interesting because I had no idea what that would look like, or if it would make any sense in terms of generating, like, I suppose if you have a text classification model, it's like generating a sequence of tokens that maximizes the classification. I'd be super interested to see like a paper on that as well and what they find. So Julian, you asked, does that suggest that fine-tuning could make a particularly big difference in this environment? If I understand your question correctly, I think fine-tuning, I would be curious as to the impact of fine-tuning on the like the generation of these prototypes and what difference it makes of them. But so I suppose like you could have like a base model trained on ImageNet, and then you fine-tune it, like you fine-tune it on like your own data set. That's sort of the standard. I don't know. Yeah, not sure.
Cool. If there are no more questions, we'll finish a little bit early. Does anyone have anyone ask? Okay. Well, thanks everyone for coming, and thanks Gerard for presenting. I'm gonna stop the recording.
Thank you, Gerard. Thank you, Peter.